Okay, hello and welcome back to Chemistry Talk. Today we will be discussing enthalpy and Hess's law and the law of summation, continuing our discussion of thermochemistry, which was the previous video, but we will be getting into some more involved calculations involving enthalpy today, or in this video. So what is enthalpy? Enthalpy is the heat of a reaction at constant pressure. So that is represented by delta H. Now, delta H doesn't always mean enthalpy because not all heats will be formed at a constant pressure. So just pay attention to that. Now, enthalpy can also be represented by delta H with a superscript there. Now, what that superscript means is that this reaction occurred at standard conditions. Now that's important. A lot of times teachers and professors will ask about that because that little superscript means that our enthalpies occurred at what we call standard conditions. So it's constant pressure, constant temperature, and that's important because sometimes when you observe reactions, you won't get a congruent delta H. That's because they didn't occur at perfect standard conditions. So that's what that superscript means. So as a review, exothermic reactions release heat. They have a net loss of heat. They have a negative Q, or a negative delta H. Endothermic reactions absorb heat. They have a net gain of heat, a positive Q. Now, if you notice here, these reactions look very similar, but our delta H's have opposite signs. Why is that? That's because I changed our products and reactants. I flipped the reaction. So here our reactants are our products in our second reaction, and here our products are our reactants. So in summary, I basically just reversed them. Now when I reversed them, I changed the sign of my enthalpy, and that's all good. You just have to flip the sign. No big deal. You can just switch them around and flip the sign. So this now became an endothermic reaction. This is another example of that. Here we have the decomposition of water. It's endothermic. It absorbs 136.6 kilocalories of heat. But if I flip the reaction, it's now exothermic. It's releasing heat. And this is now the formation of water. So the sign switched when I flipped the reaction. And that's the biggest concept here. So what you can also do is make a proportion. The amount of enthalpy is directly proportional to the amount of reactant or product. So if I want to know how much heat is released by 1 mole of water, I'm going to divide this whole reaction by 2, which is the same reaction here, the formation of water. I'm going to divide the whole reaction by 2 to just get 1 mole of water. So if I divide the whole reaction by 2, I have to divide the enthalpy by 2. So when I do that, I get 1 mole of hydrogen, half a mole of oxygen gas, it's okay to have fractional coefficients, form 1 mole of water, and I divided the enthalpy by 2, so I got negative 68.3 kilocalories of heat. Now, what this superscript of open sign also means is that you're using the table values. These are the recorded values at standard conditions. So here is the recorded values at standard conditions for the formation of water, 1 mole of water. But notice that these numbers are different, but we're forming water. Why? One of them is water vapor and one of them is liquid water. So liquid water and water vapor have different heats of formation. Now, that was direct methods of calculating enthalpy. This is an indirect method, and that's known as Hess's law. That says that when reactants are converted into products, the enthalpy changes the same whether the reaction takes place in one step or a series of steps. So the sum of the steps should equal the reaction, and let me show you what I mean by that. I'm asking you to calculate the heat of the formation of methane given the following information. So to form methane, we take solid carbon and we add hydrogen gas, 2 moles, and we get methane. So the reaction takes place in steps. Now we can use these enthalpies or heats of formation to calculate the delta H for this reaction, but we have to make sure that our reactants and products are on the right side. So in all of these, carbon and hydrogen should be on the left side, the reactant side, and methane should be on the product side. Now we may have byproducts or products or reactants that cancel, and we're not going to worry about those. We're just concerning ourselves with these three compounds and elements. So let's check our first one. We have carbon plus oxygen gas gives us carbon dioxide. So we're just concerned with carbon, and it is on the reactant side, so that's good. Here we have 2 moles of hydrogen gas plus a mole of oxygen gas gives us 2 moles of liquid water. We're concerned with the hydrogen, and it's on the right side, so that's good. Here we have methane plus 2 moles of oxygen gas gives us carbon dioxide and water. This is not good because methane should be on the product side, not the reactant side. So we're going to have to flip this reaction. So when we flip it, what we get is carbon dioxide plus 2 moles of water form methane gas. So now methane's on the product side, and 2 moles of oxygen gas. So remember, if we flip the reaction, we also have to flip our heats of formation. So now the heats of formation of this reaction is positive 890.4 kilojoules because we reversed it, and that's what we needed to do. So now we can calculate the enthalpy change for this reaction. But first we have to make sure that we did this correctly. So to do that, we're going to write this reaction. So I'm going to take all our reactants and all our products, and when everything is simplified and canceled, we should get our original reaction. So here I have carbon plus 2 moles of oxygen gas plus 2 moles of hydrogen gas plus carbon dioxide and 2 moles of water. So those are our reactants. Now let's look at our products. Carbon dioxide gas again, water, 2 moles of water, and methane, and 2 moles of oxygen gas. Now if we did this correctly, we should get some spectators, things that cancel out. So let's take a look. Here I have 1 mole of carbon dioxide. Here I have 1 mole in the products and reactants, so that can cancel. I have 2 moles of water here and 2 moles of water here, so that can cancel as well. And what else? Okay, I have 2 moles of oxygen gas in the reactants and 2 moles of oxygen gas in the products. So what am I left with? Solid carbon plus 2 moles of hydrogen gas give us one product, which is methane gas. Now would you look at that? That is our reaction. So that means we did this correctly, but we're not done. We just flipped our reactions. Now we have to calculate the enthalpy. So we're going to take the sum of the changes we made, so negative 393.5 kilojoules plus negative 571.6 kilojoules plus, now look, we flipped our sign here, 890.4 kilojoules. So we get our final delta H of our reaction to be negative 74.7 kilojoules. And that is our final answer. So that is the delta H for that reaction. Why did I go through the step of writing this reaction? I needed to make sure that our products and reactants were on the right side. If I didn't go through this step and I didn't reverse this reaction, the carbon dioxide in the water wouldn't have canceled here, and we wouldn't have gotten our original reaction, and this answer would be wrong, and I wouldn't have realized. But I realized that we did it correctly because I switched this, and you can catch your mistakes by doing this step here. And that's our final answer. All right, the combustion of, example 2, the combustion of butane proceeds as follows. 2 moles of butane plus 13 moles of oxygen gas give us 8 moles of carbon dioxide gas and 10 moles of liquid water. And the delta H here is negative 5.8 times 10 to the third kilojoules. I want to know the heat of this reaction. Okay, well, let's see what we have. So here, I noticed that we flipped it. Our reactants here are our products here, and our products in the original reaction are our reactants here. So we flipped the reaction, which means we need to change the enthalpy sign. We need to make this a positive 5.8 times 10 to the third kilojoules. Now, is that it? No. There's another thing that happened here. And the telltale sign of this is the 2 here. We divided the entire reaction by 2, or this reaction by 2, rather. So what do you get? Whoops, did that again. It's okay. We divided this whole reaction by 2. So that gives us 4 moles of carbon dioxide gas, 5 moles of water, 1 mole of butane, and 13 halves of oxygen gas because we divided everything by 2. But we also flipped it because our products here are reactants here, and our products here are our reactants here are our products here. So first, we flipped it, which means that we're going to change the sign from negative to positive 5.8 times 10 to the third kilojoules. But we also divided the reaction by 2, which means we have to divide our enthalpy by 2. So our final enthalpy is 2.90 times 10 to the third kilojoules. So in summary, our products here are now our reactants. So we flipped the reaction, which means we changed this sign to positive. But we also divided the coefficients by 2, which is signaled by here, this 2 here, this fractional coefficient. So we need to divide the enthalpy by 2. So that's how we got our final answer. So another way to calculate heats of a reaction, or enthalpy, is using the law of summation. And this says that the heat of reaction using the, here we're using table values by that. So the heat of a reaction is equal to the sum of the heat of the products of the reaction minus the sum of the heat of the reactants. So if I had a reaction A plus B gives me AB the heat of AB, So the heat of the products minus the heat of the reactants, and it's the sum of the heat of the reactants. That's what the sigma symbol means, because we have two reactants, gives us the total heat of the reaction. And that's what the law of enthalpy summation means. So let's see an example of this. Given the balanced combustion of methane and the following information, what's the standard heat of formation of methane? Standard, we're using the table values. Okay, so let's see what we're given. We are given our total reaction, so the combustion of methane, 1 mole of methane plus 2 moles of oxygen gas give us 1 mole of carbon dioxide gas and 2 moles of liquid water. And this is our standard heat of formation. But we're also given the heat of formation of liquid water and the heat of formation of carbon dioxide. So what we're actually solving for is the heat of methane by itself. So that's our reactant. So we could say that the heat of the reaction, which is given to us, it's that number there, equals the sum of the heat of the products minus the sum of the heat of the reactants. And that's what we're actually solving for. We're solving for the heat of the reactants, or methane. So let's find the heat of the products. We have 2 moles of water. So we're going to times 2 times 2, negative 285.8. And we have 1 mole of carbon dioxide, so plus negative 393.3 kilojoules. So our heat, or the sum of the heat of the products, equals that sum. So that would be, let me do the calculation here. That would be negative 964.9 kilojoules. So now let's plug in what we know. We know the heat of the total heat of the reaction is negative 889.1 kilojoules. And we know that equals the sum of the heat of our products, and that's negative 964.9 kilojoules. And we're solving for the heat of our reactants, which is methane. So to solve for this, I'm going to add 964.9 to the other side. So this cancels here, and I'm going to add 964.9 kilojoules. And that gives me 75.8 kilojoules equals negative heat of our reactants. So that is a little bit of a problem because we have this negative sign here. So I'm going to multiply the entire equation by -1. So we get the heat of our reactants or methane to be negative 75.8 kilojoules because we multiplied it by -1. And that is our final answer. The diatomic molecules, such as oxygen, their heat of formation is 0. So that's why the heat of our reactants is just methane, and that's negative 75.8 kilojoules. And that's using the law of enthalpy summation. So I hope this helps you to understand Hess's law and the law of enthalpy summation. Comment if you have any questions or requests, and our next video will be on our way. Thank you.